Strain measurement is a cornerstone of engineering and materials science. It allows us to understand how materials deform under stress. This knowledge is crucial for designing safe and reliable structures. From bridges to airplanes, understanding strain helps ensure structural integrity. Accurate strain measurement is essential for predicting material behavior. Strain is defined as the change in length divided by the original length. It's a dimensionless quantity, often expressed as a percentage or microstrain. Measuring strain allows us to quantify the deformation of a material. This information is vital for assessing structural health and performance. Strain measurement techniques vary depending on the application and material. Various methods exist for measuring strain, each with its own advantages and limitations. Strain gauges are among the most common and versatile tools. These small sensors adhere to the surface of a material. They convert changes in length into electrical signals, allowing precise measurement. Other methods include extensometers, optical techniques, and digital image correlation. Strain measurement is not just about measuring deformation, it's about understanding material behavior. By analyzing strain data, engineers can predict how structures will respond to various loads. This knowledge is crucial for preventing failures and ensuring long-term performance. Strain measurement also plays a vital role in research and development of new materials. Strain gauges are the workhorses of strain measurement. They offer a simple yet effective way to quantify material deformation. These small sensors are bonded directly to the surface of a material. As the material stretches or compresses, the strain gauge deforms along with it. This deformation alters the electrical resistance of the gauge, providing a measurable signal. Strain gauges come in various types, each designed for specific applications. The most common type is the electrical resistance strain gauge. These gauges rely on the principle that a conductor's resistance changes with its length and cross-sectional area. Other types include semiconductor strain gauges, fiber optic strain gauges, and piezoelectric strain gauges. Each type has its unique advantages and limitations in terms of sensitivity, temperature range, and cost. The performance of a strain gauge is characterized by several factors. Gauge factor, a measure of sensitivity, indicates how much the resistance changes for a given strain. Temperature compensation is crucial, as temperature changes can affect the gauge's resistance independent of strain. Linearity describes how well the gauge's output corresponds to the actual strain. Hysteresis refers to the difference in readings when the strain is applied and removed. Understanding these characteristics is essential for selecting the right gauge for a specific application. Strain gauges find applications in a wide range of industries. They are used in structural health monitoring of bridges and buildings. They play a crucial role in aerospace engineering for testing aircraft components. In automotive engineering, they're used to analyze stress and strain on vehicle parts. Strain gauges are also essential tools in biomechanics research for studying the forces acting on bones and tissues. Electrical resistance strain gauges are the most widely used type of strain gauge. Their popularity stems from their simplicity, versatility, and relatively low cost. These gauges consist of a thin metallic foil or wire arranged in a grid pattern. The grid is bonded to a flexible backing material, typically polyimide. This backing allows the gauge to conform to the surface of the tested material. When the material deforms, the metallic grid stretches or compresses, changing its resistance. The construction of electrical resistance strain gauges is carefully designed to optimize performance. The choice of metal for the grid depends on the desired sensitivity and temperature range. Constantan, an alloy of copper and nickel, is commonly used due to its low temperature coefficient of resistance. The grid pattern is designed to maximize sensitivity to strain in a particular direction. The backing material must be flexible yet durable, providing good adhesion to the tested material. Adhesives play a critical role in the performance of strain gauges. The adhesive bonds the gauge to the material, ensuring that it accurately reflects the material's deformation. The adhesive must be strong enough to withstand the applied loads and environmental conditions. It should also have good electrical insulation properties to prevent current leakage. Choosing the right adhesive is crucial for obtaining accurate and reliable strain measurements. Mounting methods for strain gauges vary depending on the application and the type of material being tested. Surface mounting is the most common method, where the gauge is simply bonded to the surface of the material. Embedded strain gauges are placed within the material itself, providing measurements from within the structure. Weldable strain gauges are designed for high-temperature applications and are attached by welding. Proper mounting technique is essential for ensuring accurate and reliable strain measurements. Analyzing strain gauge data is crucial for understanding material behavior and structural performance. The raw data from strain gauges represents changes in electrical resistance. This data must be converted into meaningful strain values. This conversion involves using the gauge factor, a calibration constant specific to each gauge. The gauge factor relates the change in resistance to the actual strain experienced by the material. Calibration procedures are essential for ensuring accurate and reliable strain measurements. Once the strain data is converted, it can be analyzed to determine various mechanical properties. Stress, the force per unit area, can be calculated from strain using the material's elastic modulus. This allows engineers to assess the load-bearing capacity of structures. Strain data can also be used to determine the yield strength, the point at which a material begins to deform permanently. Understanding these properties is crucial for designing safe and reliable structures. Environmental effects can significantly influence strain gauge measurements. Temperature changes can affect the gauge's resistance, leading to errors in strain readings. Temperature compensation techniques are employed to mitigate these effects. Humidity can also affect the adhesive bond and the gauge itself. Protecting the gauge from moisture is essential for maintaining accurate measurements. Understanding and accounting for environmental factors is crucial for obtaining reliable strain data. Interpreting strain gauge data requires careful consideration of the experimental setup and the material's properties. The location and orientation of the strain gauges influence the measured strain. The material's Poisson's ratio, which relates lateral strain to axial strain, must also be considered. Proper data interpretation allows engineers to gain insights into the material's behavior under various loading conditions. This information is crucial for optimizing designs and ensuring structural integrity. Section 5. Exploring non-destructive testing methods. Non-destructive testing, or NDT, methods play a vital role in assessing the integrity of materials and structures without causing damage. These techniques allow engineers to detect flaws, measure material properties, and evaluate structural performance. NDT methods are widely used in various industries, including aerospace, automotive, and civil engineering. They are essential for ensuring safety and reliability in critical applications. Different NDT methods rely on different physical principles, each with its own advantages and limitations. Load testing on structures is a common NDT method used to assess their strength and stability. Controlled loads are applied to the structure while strain gauges and other sensors monitor its response. This allows engineers to determine the structure's load-carrying capacity and identify any weak points. Load testing is crucial for validating design calculations and ensuring structural integrity. It is routinely performed on bridges, buildings, and other critical infrastructure. Ultrasonic testing utilizes high-frequency sound waves to detect flaws and measure material thickness. The sound waves are transmitted through the material, and their reflections and transmissions are analyzed. Changes in the sound wave patterns indicate the presence of cracks, voids, or other defects. Ultrasonic testing is widely used for inspecting welds, castings, and forgings. It is a versatile technique that can be applied to a wide range of materials. Holography is an optical NDT method that creates three-dimensional images of objects. A laser beam is split into two beams, one illuminating the object and the other serving as a reference. The interference pattern between the two beams is recorded on a holographic plate. When the plate is illuminated with the reference beam, a three-dimensional image of the object is reconstructed. Holography can be used to detect subtle surface displacements and deformations, making it suitable for strain measurement and flaw detection. Section 6. Photoelasticity stress analysis through light. Photoelasticity is a powerful optical technique used for stress analysis. It relies on the phenomenon of birefringence, where certain materials exhibit different refractive indices depending on the direction of light polarization. When a stressed photoelastic material is placed between two polarizers, the light passing through the material experiences different phase shifts due to the varying stress distribution. This results in colorful interference patterns that reveal the stress distribution within the material. The stress optic law governs the relationship between stress and birefringence in photoelastic materials. It states that the difference in principal stresses is directly proportional to the fringe order observed in the interference pattern. By analyzing the fringe pattern, engineers can determine the magnitude and direction of stresses within the material. Photoelasticity is particularly useful for analyzing complex stress distributions in components with irregular shapes. Stressed models placed in a polariscope, an instrument used for photoelastic analysis, reveal intricate interference patterns. The polariscope consists of a light source, two polarizers, and the stressed model. The light source emits polarized light, which passes through the first polarizer. The polarized light then interacts with the stressed model, causing birefringence. The second polarizer analyzes the resulting light, revealing the interference pattern. By rotating the polarizers, different aspects of the stress distribution can be visualized. Photoelasticity has numerous applications in engineering and materials science. It is used to analyze stress concentrations in machine parts, such as gears and shafts. It is also employed in the design of pressure vessels and other structural components. Photoelasticity is a valuable tool for optimizing designs and ensuring structural integrity. It provides a visual and intuitive way to understand stress distributions in complex components. Section 7. Material testing experiments. Unveiling mechanical properties. Material testing experiments are essential for determining the mechanical properties of materials. These experiments provide valuable data that informs design decisions and ensures the safe and reliable performance of structures. Various types of tests are conducted to assess different aspects of material behavior. These tests are performed under controlled conditions to ensure accurate and repeatable results. Understanding material properties is crucial for selecting the right material for a specific application. Buckling tests are conducted to determine the critical load at which a slender structure will buckle or collapse under compressive stress. The test involves applying a compressive load to a specimen and observing its deformation. The buckling load is the point at which the specimen experiences a sudden and significant change in shape. Buckling tests are essential for designing columns, beams, and other structural elements subject to compressive loads. Creep tests evaluate a material's tendency to deform permanently under sustained stress at elevated temperatures. A constant load is applied to the specimen and its deformation is measured over time. Creep is a time-dependent phenomenon, and creep tests provide insights into the long-term behavior of materials under stress and temperature. Creep tests are essential for designing components that operate at high temperatures, such as turbine blades and nuclear reactor components. Fatigue tests assess a material's resistance to failure under cyclic loading. The specimen is subjected to repeated cycles of stress, and the number of cycles to failure is recorded. Fatigue failure can occur at stress levels significantly lower than the material's ultimate tensile strength. Fatigue tests are crucial for designing components that experience cyclic loading, such as aircraft wings and automotive parts. Section 8. The interplay of strain measurement and material testing. Strain measurement and material testing are intrinsically linked. Strain measurements provide crucial data for material testing experiments. By measuring the strain experienced by a material under various loading conditions, engineers can determine its mechanical properties. This information is essential for understanding material behavior and predicting its performance in real-world applications. The combination of strain measurement and material testing provides a comprehensive understanding of material behavior. Material testing experiments rely on accurate and reliable strain measurements. Strain gauges and other strain measurement techniques are used to monitor the deformation of specimens during testing. This data is used to calculate stress, strain, and other mechanical properties. The accuracy of strain measurements directly impacts the reliability of material test results. Proper strain measurement techniques are essential for obtaining meaningful data from material testing experiments. The interplay between strain measurement and material testing enables engineers to optimize material selection and design. By understanding the relationship between strain, stress, and material properties, engineers can select the most appropriate material for a specific application. They can also optimize designs to minimize stress concentrations and prevent failures. The combination of strain measurement and material testing leads to safer and more efficient designs. Strain measurement and material testing are essential tools for advancing material science and engineering. By continuously refining these techniques and developing new testing methods, researchers can gain deeper insights into material behavior. This knowledge drives innovation in materials development and leads to the creation of stronger, lighter, and more durable materials. The ongoing development of strain measurement and material testing techniques pushes the boundaries of engineering and material science. Section 9. Advancements and future directions in strain measurement. Advancements in sensor technology are revolutionizing strain measurement. Fiber optic sensors offer high sensitivity, immunity to electromagnetic interference, and the ability to measure strain over long distances. These sensors are becoming increasingly popular in structural health monitoring and other applications. Nanotechnology is enabling the development of miniature strain sensors with enhanced sensitivity and resolution. These advancements are expanding the possibilities of strain measurement. Digital image correlation, or DIC, is a non-contact optical technique that is gaining prominence in strain measurement. DIC uses high-resolution cameras to capture images of a material surface before and after deformation. By comparing the images, the software calculates the strain distribution across the surface. DIC offers advantages in measuring large strains and complex deformation patterns. It is becoming increasingly important in various fields, including materials science and biomechanics. Wireless strain sensors are eliminating the need for cumbersome wiring, making strain measurement more convenient and versatile. These sensors transmit data wirelessly to a receiver, allowing for remote monitoring and data acquisition. Wireless strain sensors are particularly useful in applications where access to the measurement location is limited. They are finding applications in structural health monitoring, aerospace, and other fields. The integration of artificial intelligence, or AI, and machine learning is transforming strain data analysis. AI algorithms can analyze large datasets of strain data to identify patterns, predict failures, and optimize designs. Machine learning can be used to develop predictive models for material behavior under various loading conditions. These advancements are enhancing the efficiency and accuracy of strain data analysis, leading to more informed decision-making. Section 10. Conclusion. The enduring importance of strain measurement and material testing. Strain measurement and material testing are essential for ensuring the safety, reliability, and performance of engineered structures and components. From bridges to aircraft, accurate strain measurements and comprehensive material testing are crucial for validating designs and preventing failures. These techniques provide invaluable insights into material behavior under various loading conditions. They enable engineers to make informed decisions regarding material selection, design optimization, and structural health monitoring. The importance of strain measurement and material testing extends beyond traditional engineering disciplines. These techniques are finding increasing applications in biomechanics, medical device development, and other fields. Understanding the mechanical behavior of biological tissues and materials is crucial for developing new medical treatments and devices. strain measurement and material testing play a vital role in advancing healthcare and improving human well-being. As technology continues to advance, strain measurement and material testing techniques will become even more sophisticated and powerful. New sensor technologies, advanced data analysis methods, and innovative testing procedures will further enhance our understanding of material behavior. These advancements will lead to the development of stronger, lighter, and more durable materials, enabling further progress in engineering and other fields. The enduring importance of strain measurement and material testing lies in their ability to provide critical information about the mechanical behavior of materials. This knowledge is fundamental to the design, construction, and maintenance of safe and reliable structures and components. As we continue to push the boundaries of engineering and explore new frontiers in materials science, strain measurement and material testing will remain indispensable tools for innovation and progress.